Hello friends, now this is the derivation part of lecture number 8.1 that was related to density of states. This density of state is just the total number of states per unit energy per unit volume. So in order to derive this density of state for any solid system or for semiconducting materials, we have to follow certain steps. So I should start from the concept of one electrons in infinite potential well, and I will consider first the one-dimensional case, then it will be generalized for three-dimensional case. So let us have the similar calculation we have performed in the case of Schrodinger equation, where we have used the application of Schrodinger equation in a free particle inside a box, infinite, having infinite potential at the wall. So let us have this constant potential well. This is the size of this potential well is A, let's say. So here this is x is equal to 0 and this is x is equal to A, and the potential is infinite in this wall, and here that potential energy U, it is equal to 0 as usual, and one electron is inside confined in this box. So we can use that Schrodinger equation. So from Schrodinger equation we have del square psi by del x square plus 2m by h cross square E minus u psi it is equal to 0. Since this potential energy u is 0 in this case, so one can write this is del x square plus 2m by h cross square E psi it is equal to this, which we can further write like this: del square psi by del x square plus k square psi, this is equivalent to 0, where this k it is equivalent to 2 pi by lambda, which is here substituted as equivalent to 2me this by h cross square in the under root. So this is the simple differential equation, and solution of this is differential equation is the solution of this differential equation is just taken as psi is equivalent to a constant A multiplied by sine kx plus b cos kx. So we have used a similar solution there also. So again we have to use the boundary condition to find the value of this coefficient A and B here. So we have two boundary conditions again here. So at the wall, this is the infinite potential wall. So by using boundary condition that at x is equal to 0, the psi is equal to 0. So as in turn we will have this by using this 0 it is equivalent to A sin k multiplied by 0 plus b cos k multiplied by 0, and this is not equivalent to 0, this is equivalent to 1. So this gives that this is equivalent to b is equivalent to 0. So by using the first boundary condition we have the output as b is equivalent to 0. Now we will use the second boundary condition. Then we have the second wall of this one-dimensional potential well. So this is the first one, now this is the second one. At x is equivalent to A, again this wave function psi is equivalent to 0. So here this is 0, it is equivalent to A sin k A. So this implies this ka it is equivalent to n pi, where n is equivalent to plus minus 1 plus minus 2 and so on. So this k, it is equal to n pi by a. This is the value of this k, and we can convert this k in form of energy. So this energy, we have this k, it is equal to root of that energy, E is equal to h cross k square by 2m. This is that energy term, and this k can be substituted here. So this is n square pi square h cross square by 2m. This is that energy. So we have this wave function psi, it is equal to this a multiplied by sine n pi by a multiplied by this x. So this is the wave function psi, and this is that energy eigenvalue, and for different value of n, we will have different discrete energy levels here. So for n is equal to 1, just by putting 1, 2, 3, and we can have different energy value. And for psi, if we want to plot this psi here, then this is the psi is equal to 1, and again for psi n is equal to 2, we will have another wave here. So let's see the plot. How can we get this? This is x is equal to 0, this is x is equal to a. So this is n is equal to 1, n is equal to 2, n is equal to 3, and so on. So since we have this k, it is equal to n pi by a, and we also know this k is equal to 2 pi by lambda. So by comparing these two, lambda, it is equal to, so pi can be cancelled here. So by comparing these 2 pi by lambda, it is equal to n pi by a. So a, it is equal to n upon n lambda by 2. So here when we put n is equal to 1, so this is half lambda. When we put this n is equal to 2, n is equal to 2, then that is equal to lambda. So we will have like this, and when we put this n is equal to 3, then we will have this this is 2, and there will be 3, like that. So we can easily plot this wave function psi for different value of n. And similarly, this probability density can be also plotted here. This is probability density. Again, this is for n is equal to 1, n is equal to 2, n is equal to 3. So this is n is equal to 1, n is equal to 2, n is equal to 3, and this is psi square along this, x is equal to 0 and x is equal to a. So here this is the maximum probability at the center, and just we have to put n is equal to 1, and the different value of x, those maximum probabilities at the center of this, and we will have this is the second probability. So here the equal probabilities existence of electrons, it is somewhere here, this a by 4 and 3a by 4, and this is the third one. So like this. So this is the plot of the probability density for one-dimensional case. Now we can generalize this for a three-dimensional case, because we have to consider that density of state in a solid crystal. So we have to use that three-dimensional case. So in 3D potential wave, we have to generalize the same. So the Schrodinger equation can be written as equivalent to, for the one dimensional we have just del square. So this is a del square psi del x square plus del square psi by del y square plus del square psi by del z square. This is three dimensional, plus 2m by h cross square E, and I am directly putting here that that energy, that potential energy U is 0. So this is E psi, it is equal to 0. In terms of k, so this is one can write this E x y z in three dimensional case. So this is del square psi by del x square plus del square psi by del y square plus del square psi by del z square, plus this is k square psi, it is equal to 0. where this k is square, it is actually the sum of the component of this x, y, z. So kx square plus ky square plus kz square. This is for the 3D case. And for the solution, we use the different method here. So we can put this psi as a different multiplication of different wave function in different direction. So by Division method, this wave function psi at x, y, z, it is written as equivalent to psi along x-axis, psi along y-axis, and psi along z-axis in the multiplication form, where one can write by using the similar method, similar boundary condition. We will have this constant a, and this is sine kx x and sine ky y multiplied by sine kz z, where this kx, ky, and kz can be written as equivalent to this, where kx can be written as equivalent to nx phi by a, if the size of that potential wave along x-axis is a, and ky, that is equal to ny pi by b, if the size along y direction is b, and that kz, it is equal to nz pi by c. So if we are considering three-dimensional case, so a, b, c, these are the components along the size of that box along that box, it is ABC. So this k square, the energy terms, that E can be written E x y z, that can be equal to, we have general formula is what is that, that is h cross square k square by 2m. So here this is the kx square plus ky square plus kz square, and this is h square by 2m, and we can put kx, this is n pi square nx square pi square by a square, and plus ny square pi square by b square plus nz square pi square by c square, and this is that energy terms in three-dimensional cases. So here we use one concept that is known as the concept of that k space. So in place of particular direction, we use the concept of k space here, because in one-dimensional case we have a discrete level like this. So this is, let's say, energy E, and this is that energy K. Then we have different discrete lines here. This is pi by a, this is 2 pi by a, this is 3 pi by a, and this is 4 pi by a. This is along x-axis, and the negative sign will be minus pi by a, minus 2 pi by a, like this. So these are the discrete lines in k points along x-axis only. So when we consider two-dimensional, three-dimensional case, then we will have this pi by b, pi by c, pi by in y direction, pi by c, 2 pi by c in the z direction. So we have this k space, the concept of k space, and what is the need of this k space, and we will discuss in separate lectures when we will talk about the bend concept of bend diagram, formation of bend diagram, and the EK plot. So here this k space is just a three-dimensional space where there is a probability of existence of that so this is kx, this is ky, and this is kz. So in place of x, y, z, we will use kx, ky, and kz, and this type of surface, another term we will use, that is known as a Fermi surface. So we will use a Fermi sphere. Fermi sphere, this is the maximum size of a sphere up to which the existence of electrons can be imagined. So this is the Fermi surface, and corresponding that radius, this is taken as equivalent to kf. So for a system, a single electron, let us make some separate diagram for that, and try to calculate that density of state. So I'm using one small part of that K space, and this is that small part, three-dimensional part, and this is along x-axis, this is kx, and this is ky, and this is kz. And if we consider that ordinary three-dimensional space, then we take this is equal to A, this is equal to B, and this is equal to C. But here this is K space, so this point and this point, this will be pi by A along x-axis, and this will be pi by B along y-axis, and this will be pi by C along z-axis. And one reciprocal lattice term is used in solid physics. Reciprocal lattice, it is used in solid physics. So what is this reciprocal lattice, and what is the importance of this reciprocal lattice, I will discuss in separate lecture. So here this size is pi by A, pi by B, and pi by C. So one can calculate the volume of this small site where one electron is inside this, and this is actually the part of the Fermi sphere. Let us have, this is the Fermi sphere. So the size of this radius is, this is kf, and the probability of the existence of that particular electron is up to this highest surface. This is known as Fermi surface, and this is Fermi sphere. So now let us try to calculate the volume of these two. So the volume of this single site, a single, let's say single state. So we are just taking one small part where one electron is here. So this is the single state. So we can calculate the volume of this single state, that is V single state. It is equal to, the length is pi by A, and pi by B, and pi by C. So the total volume is, this is equal to pi cube by A dot B dot C, and one can write this is equal to pi cube by V. V is the size of the total volume of that this space. So we can generalize this as V. Now we can also calculate the volume of Fermi sphere. So this is V Fermi sphere. This is equal to just one spherical system. So this is 4 pi by 3 kf cube, where this kf is the radius of this Fermi sphere. And now we can try to calculate some numbers of states by using these two volumes. So n, that is the number of state, field state, the number of, this is field state in Fermi sphere. So this is the maximum, outer surface is the maximum level where electron is filled, but we can calculate the number of field state inside this Fermi sphere, which is denoted by capital N here, and this is equal to volume of this Fermi sphere upon volume of, this is small single site. So volume of single site, small single site, single state, and we will further multiply it by 2 because by using Pauli's exclusion principle, in one state there will be 2 electrons, so we will include here a term 2, and it is further multiplied by 1 upon 8. So 1 upon 8 is introduced here because of we are taking the positive part of nx, ny and nz. So similar to that two-dimensional case, we have the 4 coordinates here, and this coordinate is positive. So this is one coordinate, 1/4, 1 by 4 we take. So in case of three-dimensional case, we have where we are taking this nx, ny and nz, and these are in positive, negative in different direction. So since we are just considering the positive part, so one octave is used. That's why we are using this 1 upon 8 term here. So let us put the value of this 2 and try to calculate some more. So I think I should remove this. So this n is equal to it is equal to volume of Fermi surface is 4 pi by 3 kf cube by volume of single state, that is equivalent to pi by a, pi by b. So this is pi cube by v, where v is equivalent to a dot b dot c, and we are including here this 2 multiplied by 1 upon 8. So one will have this this can be cancelled out. So 1 by 3 is here and pi is here. 1 pi is cancelled out. So n it is equal to now kf cube multiplied by v. This kf cube multiplied by v upon 3 pi square. So this is n, the total number of states, filled state in that Fermi sphere. And now we can further calculate it for kf. So this implies kf it is equal to 3 pi square n by v of 1/3. This is in cubic form, so we just sitting here 3 pi square and multiplied by n upon v, so 1/3. And why we are calculating this kf? Because we want to calculate that energy EF. Since EF it is equivalent to h cross k f square by 2m. So this is the term h cross k square by 2m, and we are putting here this kf. So this EF can be written as equivalent to h square by 2m, and this kf is this is 3 pi square n by v, and it is in square terms, so this is 2 by 3. So this is EF energy can be calculated like this. And one can also, this n upon v can be replaced by the single n. So this is h square by 2m. So this is 3 pi square n by 2 by 3, where n is equivalent to capital N by v. This is the density of electrons. So this is EF and this is KF, and now we have to finally calculate the density of state. So for the density of state we need this n, and KF we can replace. So first let us have again that original value of n. So again let us put n is equal to, so this is v by 3 pi square kf cube. So this v is this term, and this is 3 pi n is here. Okay, so we have this k, it is equal to in terms of energy, this is 2me by h cross square. So we can put here this kf or k. So this implies this n is equivalent to v by 3 pi square, and kf is this. So this is 2me by h cross square, and this is half, so this will be 3 by 2. So n is equivalent to v by 3 pi square and 2me by h cross square 3 by 2. Now we have to define that density of state, and the density of state is defined as represented by ZE or DE. This is equivalent to dN by DE, the total number of field state per unit energy upon per unit volume. So this is dN by dE upon capital V. So this is the value of n, and we have to calculate dN by dE and put here and find this density of state. So let us calculate dN. So this implies dN by dE is equal to, so this is V by 3 pi square, and by differentiating this is multiplied by 3 by 2, and 2me by h cross square half multiplied by 2m by h cross square. This is the differentiation part, and we can put here. So this 3 can be cancelled, and that ZE, the density of state, this is equal to V upon 2 pi square. The 2 can be also cancelled here. So this is Vm upon pi square h cross square 2me by h cross square half, and this is divided by V. So V can be cancelled from this, and here this m, there is m in power of half, and there is 2 pi square h cross square. So this there is one h here, so one can generalize this relation as constant. So root of 2, this is m 3 by 2, and this is root of e by pi square, and this is h cross q, or h square, that's 3 by 2 one can write. So one can say this is just proportional to the square root of energy. So this is for the general solid materials, and if you want to use the same for semiconductor material, then we will replace this m by, that is effective mass, and e, that e will be replaced by, for semiconductor that e is, it is replaced by either e minus ec or ev minus ec, depending on that conduction or valence bank, and this m, this is replaced by that effective mass. So what is that effective mass and how this is, that will be included in the next lecture. So this is the final calculation of density of state. Thank you all, and maybe some mistakes in calculation is possible because this is too complicated. So try to calculate yourself, and if there is some error, then just give the feedback. Okay, thank you.